Hello, everyone. So uh, I've made significant progress since the last live proving stream. Let's see where we're at. This is a kind of a dependency graph of the files in my project here. So I have this arithmetic sequences thing. I have the notion of a prime generator. I have a Prime Sieve, which is a kind of prime generator, and I have a Rake Sieve, which is a kind of Prime Sieve that uses this notion of a rake which is a collection of arithmetic sequences that all have the same slope or delta or base or whatever you want to call it. And so all of this is working, except there are some assertions or properties or theorems in this file that have not been proven yet. So they're proven with the word sorry, which just makes something true because you say it's true. It makes basically by declaring it to be almost like an axiom, and so you don't want to do that very often. Actually, I'm going to commit my code here, and I'll talk a little bit about where I'm at. But the good thing here is that see, I'm just call this work in progress. Rake work in progress. But basically, the good thing is that pretty much everything that about this data structure ought to be pretty simple to prove. But what I don't have a lot of experience proving facts about lists and data structures. Up till now, almost everything I've been doing has been like kind of abstract and talking about proving properties of prime numbers and sets and things like that. And so now I'm talking about a data structure that has, well, the way it has been working so far is that we have so the d is the delta, the slope of some lines, and the sequences are the if you imagine some lines being graphed out, well, in any place where you input an integer, you get an integer out. They're called arithmetic sequences, and so what we have is a list of them that all share the same slope. And so you can imagine parallel lines stacked up, and they're kind of like slanted with the same slope. And so to me, that's like what you would get if you dragged a rake through the sand and made a bunch of lines in parallel. So I call this structure a rake. And it has two properties: that the list of the sequences is sorted, so that the zeroth list is the bottommost one if you're graphing them, and the list is non-empty. And I'm kind of in the middle of rewriting this because well, first of all, like you have a list of arithmetic sequences. They're copying this letter D every time, but I wanted to just simplify it a little bit. So this is the current version, and this is like a hypothetical version that I'm trying to implement. And I thought I'd try and film it while I'm doing this. So right now this rake prime is not hooked up to anything, but the idea is that I'll just rewrite this in terms of this. I'll get rid of rake once this works, because they have the same properties or whatever. The thing I really want to prove, that I really need to work up to, like all these things are saying that okay, so the idea of this rake, the reason for having it is that it models, or you can configure it to model the set of numbers that have not been scratched out in your prime sieve, right? So if you're doing the sieve of Eratosthenes, you scratch out all the multiples of 2, you scratch out, first of all, anything less than 2, then you scratch out the multiples of 2, the multiples of 3, the multiples of 5, and so on for each prime number that you encounter. And this data structure gives you a way to do that. And I can prove that so long as at every step, it drops the terms it's supposed to drop, it keeps the ones it's supposed to keep, and it doesn't introduce anything new. So I expect these to be fairly simple proofs. Crossing your fingers, who knows, in Lean. But conceptually, they're very simple, and you just have to prove that those invariants hold for, or that those rules hold for the every operation you do. So right now those operations are dropping anything greater than or equal to a number, or keeping everything greater than or equal to a number so that you can drop the numbers less than 2, and then also dropping multiples of a prime number, so that you can so you scratch out the multiples of a prime as you find it. And I'm not going to have time for the video I'm really trying to make, but in theory, the big downside of this algorithm, if you watch my other videos, is that in order to do this step, it multiplies the number of lists that you're keeping by the prime number. So you wind up, and then it drops like 1 minus that prime, or that prime number minus 1 of those lists. So you wind up multiplying by 5, multiplying the number of lists you have so far, which is you start with like I forget how it goes. It's like conceptually it's 2 times 3 times 2, so you wind up with like 6 lists, I guess, and then you multiply by 5, you get 30 lists, but you have to subtract 5 of them, so it's 25. But I think I'm screwing that up and not doing it right. Anyway, yeah, I should probably simplify that explanation quite a bit. But the number of lists grows more than exponentially, right? So it grows. You're not just multiplying the same number over and over again, which would be exponential growth. You're multiplying a bigger number each time, so it's a bigger prime at each number, so it's more than exponential growth. And the problem with that is, of course, that it grows way too much. But you can cap it if you do what Eratosthenes did, which is limit your prime generation to some number, right? So you're only trying to generate the numbers up to n, and so then you would never grow more than n of these things if I implemented that. I have not implemented that, so that's something I might do in the future, but I'm trying to just get this much working and then prove that it works, even though it's a horrendously inefficient algorithm. And then that'll be the foundation of my video, because it's just I'm not using this for anything. I just want to prove that it works, so that I can say I proved it works, and I can talk about the experience I had and what I learned and that kind of thing, and somebody can go look at the code. But I am kind of thinking that in the video I want to make, that I will put like a little call to action here and say, well, here's a bunch of things that you could do to extend this if anybody out there wants to jump in and work on this code base once I've introduced it to you and you understand the idea. So I'm not going to commit to doing those things myself, but maybe other people would be interested in jumping in. I might do them. I don't know. But yeah, so like a little exercise for the viewer, I guess. And maybe somebody out there, if it gets enough views, maybe somebody out there would be interested in trying an exercise or whatever. And then maybe I'd be willing to help or whatever. So that's kind of where I'm at. But so these have to be proven. And then the main other thing that is missing is this, which this is probably all garbage here, but the basic idea is this line right here, that the minimum term of the rake is 0, so that if you put because what you need to do in order to identify the next prime is you need to look at the set of numbers that you have left, and then the smallest one is the next prime. And so the theorem here is that if you plug, the rake operates as kind of like a function, and you can ask for the nth term. And so if you ask for term 0, then that should be the minimum of the set. And so if the rule is that for any number you plug in that's greater than 0, 0 is less than that number, then you're good. And in fact, you could theorem rake ascending terms or whatever are rake. We could do this by saying, oops, by. We've got to actually say what the theorem is. And if we said that 0 is, or actually, I guess you just say m is less than n, and n is less than r. We'll do this for Rake prime. R ks length. Or we could call this size, right? We could call this size, and make this something that. Well, I'll do that in a minute. Well, I'll just do it here. So if we said size is a nat, and that is equal to sequences dot length, and then here we'll call it same thing in the new structure. We'll call it this, and it'll be ks stuff. So the idea is that here we're storing sequence objects, arithmetic sequence objects that are these pairs of numbers. But since one of the items is always the same, the d is always the same. A sequence is something like k plus n times d, right? Like it's a binomial like that. And so this is what it's generating. And so you plug in the n and you get this calculation done for you. So the d is always the same, and the slope of the line is always the same. And so why store it? So I'm going to just use this. I'm just going to store a list of natural numbers and then generate the sequence on the fly if I need to. And maybe at some point I just completely get rid of the idea of this arithmetic sequence and just inline everything in Rake, because Rake is a collection of these things. But since I already have it and I'm on a time budget, then I'm just going to stick with what I have, but just generate them on the fly as I go along. I think this little thing is going to make things simpler. Anyway, so down here, where probably at this red line where it broke, so I have our size now. So now we can just say that. Then if those, so these are like hypotheses, right? So I guess we want all this stuff, right? So if m is less than n, so we're going to have some arguments m and n are natural numbers, and HMN is the hypothesis that m is less than n, and HN size, HNR is the hypothesis that, how about we'll call it size, HNS is that r is less than size. Then we can say r term m is less than r term n equals, and then this ought to be exact. So we'd have to intro this HN pos still. So I'll put this up so you can see. I'm just visualizing in my head now so I can see what it is, but I guess which is kind of progress on my part, but it doesn't help you. So here we can say, you can see what I have to prove. And it says that, as soon as I type this word by, right, I can put a blanket here, and this tells me what I have to prove. So I have to prove what I typed here, right? So now I want to introduce this thing. So it's saying n is positive, so intro the hypothesis that n is positive, kind of the naming convention that people use. And you can see that as soon as you do that, it rewrites this last line. You see the turnstile here is the last line. So the turnstile got shorter, but by moving, and this got broken into 2 lines basically. So now this is a fact in the environment. So basically the idea is that n is some natural number, and that if this is true, then we have to prove this. So we have to be able to prove this given this fact. So in order to do that, you can just assume that fact is true. If it's not true, then it doesn't matter, right? Because false implies anything. So if this is true, we in order to prove that the entire statement is true, we can just assume this is true. And that is a valid logical deduction. All right, so then we can say this. So we can say exact, and I bet if I put a question mark here, it's gonna give me this, but it doesn't. Okay, so maybe because the stuff under here is broken. Okay, so exact should do a little search, and hopefully it'll find this, but maybe it won't. No, it can't. Okay, so then we have to have this. So we have R as a rake, M and N are natural numbers. So have HMN. Actually, well, let's just say let M equal, or actually we'll say set M equals 0. And you can see now, as soon as I did that, it rewrote this, all these zeros as M. That's what the word set does. The word, you can say let, and it doesn't rewrite everything like that. You just define something called M. If you say set, then it does the same thing as let, but then it also rewrites everything where the 0 appears in terms of M. All right, so then now we can say, now I bet exact might be able to find this, because we have M is less than N. We don't have R is less than, or N is less than R size. All right, so, but we can have that. We can say have N is less than R dot size equals by unfold size rake dot size maybe. How about if I just try this? If I say R H size. Nope. Sim. Why can't you find? Okay, well, exact is finding it. So exact is there, is finding it there. Oh no, it wasn't. It was finding. It was saying you could have said exact this had that, if I can prove this. Why can't you see that? No, maybe we start with 0. Oh. We don't know this. We don't need to know this. This is not valid, right? Because term doesn't depend on the size. So I had written this earlier, or like I wrote it during this video, right? Didn't I? So I just didn't need this. We don't have this information, and it doesn't matter because term, because the idea is that you're mapping any natural number. So any natural number can be an input. So there's an infinite number of terms. So you're not limited to the size. So as long as this is true, then this is true, and then now this is easy. And I think if we say exact, yeah, this. So now we get exact this. But if we introduce this H, then we can say exact ascending terms 0n, right? Oh, H. Oh. R H and pause. You can just click this here and I'll rewrite it. Or maybe you can't. All right. I like that better. The other version was this. Right. So it's saying that basically you have to somehow capture this fact. So so I guess this would be HN pause, right? So HN pause, or we call it HN pause. proves it either way. Oh, it comes out the exact same thing. So it's either exact fun, or you can say intro and then either way. Okay. And I think if we do this, we can do that, and then we can also say lambda here. That would actually make this one shorter. All right. Yeah, either way. So now, then this would be the thing I need to prove. So what I was trying to do, in introducing this new thing, over here, my Scratch thing, I have a bunch of variations of this idea that things I've been trying that didn't work out or haven't worked out yet. So I'll just go in reverse order. So I had this idea of is ascending, and so that well, how would I say this? Like, basically, if the list is sorted, so just natural language here, natural, the informal idea behind the proof, or that I'm going for, is that you know, every one of these equations or sequences in here, in either one of these, if the list is sorted, then you want to say, then you only have to look at the first one, because they all have the same slope. So what's being sorted is the constant term. So what you're looking at is the smallest constant in the list of constants that are being multiplied by this number d. And d is, you know, so in term 0, then d is 0 for all of them, and so then the term 0 of each term is the shortest of the terms in that sequence, and then of those sequences, the one with the smallest constant is going to have the first, you know, the smallest first number. So if it's sorted, then you should, you know, then if the list of sequences or the list of constants is shortest, you know, is sorted, ascending, the very first one should be the smallest, and then that's the idea. But proving that has turned out to be kind of frustrating. So first of all, you know, to show that some time ago I had to deal with this when I first started writing this file. You know, I wrote this thing. So rather, I wrote this one, that the list of sequences is sorted by this greater than or less than greater than or equal to relationship. I don't want that. I don't want to say that at all. But what happens is that okay, hang on. What I want to say is that the list is sorted by the less than operation. Okay, and that would mean that for every pair of items, as you move, you know, the first two items, the you know, items 0 and 1, 1 and 2, you know, every pair, as you know, the sliding window of pairs within the list, that each one is less than the next one, right? So if you say less than or equal, then the list might contain duplicates, and that makes the proof harder. And so what I want to do is I want to say that it's sorted by and it's sorted, and the relationship that holds between, you know, each pair of numbers is that the one on, you know, the one that's earlier in the list is less than the one that's next in the list, and that tells you that it's an ascending list, right? Whereas what I've been able to prove so far is that it is a non-decreasing list. So at every step, it could be greater than or equal. And I don't want that. But what happens is, and I'm just going to do this for a second, if I put this and change this, so by the way, this right here is an anonymous function. So it takes two arguments, and the arguments are replaced by dots. So in K, this would be x minus x greater than less than y. In J, it would be well, it would be the same thing, but you could also write it just like that. or whatever, but so it's in Python it would be lambda x y x less than y, that kind of thing. So right, so this is this little dot syntax is a pattern matching thing that comes with Lean. All right, so what's wrong here? Well, first of all, is I don't have an instance of what it means to say that one sequence is less than another. I have a LE, so less than or equal to, but I don't have LT, so I would have to write this, right? And I would just define what LT means, right? So LT for less than. So let's say LT, and then replace this, okay? And you can see things break. And so the problem is that I want to sort this list, and now I'm using the wrong thing because I said I'm sorting by less than. And so instead, I'll sort by less than, but that's still going to break because I didn't actually sort by less than. I sorted by less than or equal to. And here's the problem. Why didn't it happen? Did not happen? Oh, this is fine. You can do this. You can do a merge sort. But then if you want to say it's sorted, you can't. You can only get the so list merge sort sorts the list correctly, no problem whatsoever. But you can't. So that works, but you can't. But this thing sorted underscore merge sort. If we look at this, you see it says for all lists, if all lists where the list is sorted by some relationship, well, okay, so it's saying this is the predicate. So we're saying for all lists, the list is sorted according to relationship R if you performed a merge sort of R and L. A merge sort based on that relationship of the list. Right, so the new list returned by this operation is sorted according to that relationship after you sorted it by that relationship. But when we look at what R is, well, I don't know how to show this. Total and transitive. But see, we're inside this block called, oh, sorry, total and transitive. So where's the start of this block? Oh, total and transitive. Okay. So variable R is total. Oh, I didn't know you could do that. I knew you could do this. I didn't know you could say variable R down here. Oh, I see. So what this is saying. So here on this line, I didn't know this was possible. If you have, it says variable and there's some implicit R relationship, and what this is saying is that like all of these are true. The elaborator mechanism has to be aware of the fact that R is a total relationship for, yes. So R takes so alpha is some type, and R is a function that takes that type, that takes two items of that type, A and or alpha and alpha, two alphas, and produces a prop, right? And so the relation, and then the proposition is about this relationship. And so what it says is that if the relation if the relationship on type X, if the relationship R on type X is total, then that means the binary relation R on X is total. That is, that for any X and Y of type X, either R X and Y or R Y and R of Y and X. So that would mean that so less than cannot be a total operation, right? Unless you know that there are no duplicates in your list. And maybe, if you were lucky, there might be something that said like there is a predicate you can have on a list. It's called no dupe list, no dupe. And then what if it said no dupe? What was I going to say? I lost my train of thought. That no dupe. I don't think there's any information about that relationship, or maybe right. You want it to be like LT trans if no, not trans, total. Right. You'd want something that said LT total, and it would have to tell you that right. So this theorem does not exist in math, but what it would be is something that said, something like is total if, or is total less than if no dupe AR. Maybe I could just define that, right? So instance, I'm kind of getting off the track. This is just an idea. Is total alpha so alpha being some type where, and then you would have to say, so is total takes two arguments, so the type, and then so we want this thing, but we want it to be less than. And then you need this. You need this thing to say no dupe I guess first you'd have to say first you'd have to have LT of the type, LT of alpha. Why is it mad here? They'll just synthesize of LT alpha, right? I can't. I don't think I can say this because no dupe is only a property of a list, and I'm sorting things inside the list, right? Because you can't, like, if there were such a thing. Oh, maybe it is. Maybe you can do this. Okay. wrong with this? Oh, I see. Yeah, sorry. These are arguments. I think maybe even theorem. Theorem no dupe is total. How about less than total of no dupe, right? Type is not a class instance. What is no dupe? No. And I maybe just yes, I think it's list no dupe. It's a proposition about a list, so you can't actually say this. I have a feeling that maybe you could kind of say it if you could say that like that alphas is a alpha is a type, or maybe you said like see, we'll say alphas is type list A, right? And then you say list no dupe alpha S, so alphas. Oh, but you can't. So why does that can't say that? It's not a type. So you say X is a list of A and list no dupe X's, right? But it's alpha, right? List of A, list no dupe X's. Yeah, I don't think I can. You know, even then it would be more like so if we said so like X's is a list no dupe, and this is what this takes a list. This no dupe alpha no, I'm screwing things up. Well, okay, whatever. The point is, like, this is messy, right? I'm not going to try and do this because there's a better way to do this, right? And the better way is that I found earlier when, like, just searching through the docs for stuff like this, is I found something called no dupe less than no it was list sorted that looks promising, but when you see it, like, you have to have is irreflective, which is basically similar to total, right? It's that you can't have, it disqualifies less than. So this is saying that if you had it sorted by less than, then there would be no duplications. But that's not what I want. I want to say if you, I want to say this, right? I want to say that if I sort it by less than or equal to, and you can't see it here, but there is behind this, and the original list had no dupe, then all right, so L is a list, and it's sorted by the less than or equal relationship, and the original. So right. So we have some definition that interesting. Okay. Well, this says if I can prove that it's no dupe and it's sorted by this, then I can get this. But I think what I want to prove, I think this is the tricky part. Right. So L dupe of, like, I want something that says that L dupe of sort or something like that. Maybe that's what this does. Maybe that's what the sorted no dupe. If I had no dupe of perm, right? Like no dupe of, maybe I don't have perm, right? Terms of list. No dupe. So I want no dupe of sort or no dupe perm. I mean, I could run it through this, right? Like, I could do this. Say dedupe. And then that would give me this. So then, so the way I would prove that, why is this mad? It's mad because, what? Because this is just not working, right? So what is this? So we do have to say less than. Okay, so instance LT these, and I left out the, just copy this line. This is the problem. Like, I try like 10 different approaches at the same time, and it's I don't finish a thought, and this seems to happen with me more. I mean, the general feature of my personality, but if we said let sequences equals sequences prime, and then we're going to pipe it through dedupe. Oh, we can just say .dedupe. No? Decidable equal. I have to have that. Decidable eq. So we have to say instance decidable eq where what? It doesn't. I gotta see. I'm trying to see what the definition of this is so I can fill it in. It's gonna be mad, right? Because so let's look up decidable eq. Let me just go click on this. Maybe I just have eq. Type expected. Got. No idea what I'm doing. So how do I see the definition of eq? Print eq. Okay. Print eq. Yes. No. Clear this error so I don't have to look at that and then print. No. There we go. Okay. Oh, it's inductive. Okay. So it has a constructor called ruffle. Don't know what I'm doing here. All right, see, I need a stack. I need my mental stack keeps overflowing. That's the problem, right? Or that's part of my problem. Well, I think this is very hard because aha. So okay. This explains this is part of the reason why I wanted to get rid of this d-sequence thing and instead just use a list of natural numbers because I think this would be easier if I did it like this. So if we use Rake prime.gte, and R is a Rake prime, and N is a nat. And before I do that, I'm going to put this back to less centering. And get rid of this. I'll put this back. Yeah. So that clears that problem. And then now we can say Rake prime. And in fact, I'll put this afterwards. Because that's kind of how I've been doing it so far. Rake prime is equal to and I'm just going to copy this. So greater than or equal to so let f is going to be same as up here, but instead of a sequence, we're going to take lambda k. Instead of a sequence, we're going to take a constant term. And then we're going to say let s is equal to, or let s become the a sequence of k and then r dot d, so the arithmetic sequence. And then we just return this. Everything now is the same. Okay. On with that. Okay. And then except we're gonna so this is gonna return. Let's say what the type of this is. This is it takes a nat and it returns a nat. Okay. No. This returns a list of I don't even need this proof. Right? This was a proof that something was holding that I don't even need. All right, so we're going to get this, and then dot k, and then that's it. Right, so it's a function from natural to natural. It's where we take s, we compose it with RD to make a arithmetic sequence, or we apply these two terms to make an arithmetic sequence. We run the greater than or equal function on that sequence, which does what we want, and then we just take the k because it's going to have the same. It leaves the delta intact. We can't prove that yet. I think I've lost the proof here, but I might have to invoke that proof later. All right, so then we say let ks is equal to r.ks.map f, and then list.merge sort we still have to sort it by that. Oh, no, wait, no, that's not the idea. It is now I can sort it here. And then the hope is that now I can say let kss equals ks, or ks prime dot dedupe. Yes, and I can say that now because this feature of decidable eq is already implemented for natural numbers, whereas it wasn't. It's not for this custom type I made, and in order to avoid this custom type having to do that, then I can just use this. All right. We can pipe it that way. I think we can even just say this. Yeah, merge sort. Okay. Now it's much simpler. It turns out that whenever you build a type to wrap something, especially if it's a dependent type like this, well, here you see D is part of the rake, and then D is also a parameter to the type of the items in the list. So this is an assertion that they all have the same D, the same D term. Whereas here, I don't have to deal with that because I just use the constant term and then the one delta term, and then later in the definitions, that's when I convert it to an arithmetic sequence, kind of on the fly. All right, so yeah, so this is much easier now. And also I don't have to do all this like .val, .property and stuff. Like, so the val is the, I'm looping through these D sequences, right? But they're just A sequences that have some extra property. So I have to take this apart at every step. I have to say that the val is the actual arithmetic sequence, and the property is the assertion that D is the same as all the other ones in the rake. So it's much simpler to just do this, to just create it on the fly. And in fact, later maybe I just inline this function completely, and then I get rid of it of ASEQ, the arithmetic sequences. But let's proceed. So now, then I have to return one of these rake primes. So let's close these up so I can see what rake prime is, but I can see it from here. So we have D equals R.D. So we just return the same delta. KS is equal to KS prime. H sort by sim. See, now I can just H unique by sim. Much easier. H size equals by sim. Oh, what am I missing? Type is not known. It's a rake prime. Oh, because I put the word sorry after it. So okay, so sim didn't work actually. All right, but let's see what we have. So now I think I still have to sort this way. And then I want to say have ks nodup equals, sorry, ks dot nodup. I'm proving that this is true. By I would think it'd be no dupe dedupe, right? But probably not, maybe not. Oh, sorry, come back here. So no dupe of dedupe, right? Come on. Yeah, this is my theorem. So it's list no dupe dedupe. So it should be apply this at ks. Oh, I have to say, so when I do it like this, right here, I have to do this. What I have, this is what it's asking me to prove. It can't see this, so I have to say dsimp. I learned how to do this today. See, now it expands, and then we can say exact. Nope. Unknown constant list no do dedupe. You have to import this. I think I have to import that. So the error went away, but maybe it just hasn't processed it yet, so maybe it'll come back. Nope. I think I'm going to break this apart and just see what happens here. So so put 2 primes here. There you go. And then this is, I think we can just inline this. Yeah. Ah. Here, count node. All right, we'll see. We'll see if this is. This is kind of why I'm doing like a separate data structure just in parallel, because I don't know how far I'm going to get down through this file before I have to back out using this approach. I think it should be easier, but I mean, I could do it in 2 passes. Like the first pass could be just skip this, skip this, skip this, skip this, skip this. All right, just get rid of that. And this is where we have the error. No, I have to sort it like this. And I still pipe it through no-do. Okay. I might still need this. But. Yeah, I think I still need this, even though I'm not applying it for right. So, oh. I can't put it together in my head, right? I gotta say no dupe. Like list sorted no dupe. This tells me what? Okay, so this is what I want. So the I think I can get what I want from here. So let's say have list sorted no dupe maybe I can have it just from this. Wait, hang on. I cannot sort it this way. I cannot do this because I cannot acquire the fact that it's sorted. Oops. You can't use have inside of a. This is a. So far, this is just a term right now. So I'm not in tactic mode. So you have only does anything inside of tactic mode. It seems to be doing something, which is surprising me. Okay, no, it doesn't. Yeah, but if I say let h unique, that's weird that I'd expect it to show up. Like it's not showing up here. I move the cursor down to this let, and then now it says h unique. If I move it here. That's weird. Okay, so but you put the cursor on this thing, and then it shows up. All right, so this tells me that it's no dupe. So I don't need that. I just need ks prime. Let h sort. So the last thing we're doing was sorting by this. So we're going to say so. This works? Why does this work? No. Let's see. Did it work or not? Okay, so I still get this. I still get this KS's. And then now I can sort by this. And now I can say, so list sorted of LE. So I can say this if the original list was sorted. So I have, so H1 is going to be, let me write down what I need. Or not write down, but have H1 list sorted, and then this is dot this. This is the function here. L, and what is L? L is ks prime prime, and how do I get that? Well, that I get because of the thing I already know, which is that list sorted merge sort. Right, so from merge sort, I can get this. I think I can just fill this in, right? It's not working, is it? Why is this mad? I didn't prove the thing yet. Yeah, just hang on. All right, and then I need H2L node So I need H2 is L node up. Which is KS prime node up. But I don't think I have I don't think I can prove this. Oh, I can. Exact R. Where's R? Can I prove this? I don't think I can. Right, and then now return this. Now I can return exact list sorted. No, I want this function. Can I do that and not know what it is? I don't. Why did that suddenly work? It said exact R before, but that's not. This is what I was afraid I didn't have this, right? I was afraid that I couldn't prove this. And I think I can't. From what I'm looking at, there's got to be some other way to prove this. Well, I don't understand why putting these in parentheses made any difference whatsoever. And I didn't understand why we would think that is this, like, why does Rake prime this? I don't get this. But can I say this? Maybe I can say this now. Oh, okay. I can say this on Nats. I can't. Wait, why would I be able to say it on Nats? That doesn't make any sense. Right, yeah, I can't. I can never say this because is total does not make sense for for less than for less than. It only works for less than or equal. Okay? And then if I have this, right? Uh, just to make sure I have, I have what I think I have. We're going to say list sorted by dot and just less than ks prime prime. Oh, but I don't know how to prove this. And if I don't have this, I don't have the term that I need to send it in here. So how do I prove this? How do I prove that there's no duplicates? There has to be something that is a property of merge sort, right? And so let's see what we have about merge sort. Perm merge sort. That makes sense. Oh. All right, so have let h perm, or we'll say we'll have h perm, we'll have this fact. Was perm ks prime, right? say equals. Let's merge sort, and the relationship is less than or equal, and that, and then KS I think I could just say KS prime prime here. KS prime prime. Yeah. Perm merge sort. Okay, so that tells me that it's a permutation, and then I think we can say no dupe of perm. No, that's saying the permutations of the list have no. List perm no dupe. No. This is looking promising. Yes, if one is a permutation, this is what I need. Right, so I need right. So this is not H unique right now. I need the type to be KS prime prime no dupe, and I want to apply that, but I. Right, so actually we have let H unique. Wait, hang on. Have. Yeah, we'll say H unique 0 is equal to. I should be using like 0 or just H unique equals. The type of that is going to be KS prime no dupe. So this line is equal to okay. Now to say that, so say that's sorry. Nope, that didn't work. Yes, okay. Now this one is going to be by exact. Oh, you should be able to find that. That's what I just saw. No dupe if. How about apply? Okay, I have this, and I have this. Oh, I need the perm fact. So Perm. H perm. L1 perm L2. This is what this says, right? H perm. Maybe we say let. Oh, that's just a proposition. It's not proven. Yes, but we have this. All right, so now we can replace this with so I need the MPR. I need the reverse modus ponens. MPR. We don't need this. It's just a term now. Okay. And that's H unique prime. And there we go. And I think we can just say see if we can shorten that. It's going to be by exact, right? So we don't need we don't need this. So we'll say H sort LT less equal, right? And then we'll even just say this. We'll just make this anonymous. This. And we don't need by exact. Whenever you say by exact, you can just remove that. And we can even put that down here. Just inline that. So now my question is, so again, we can maybe instead of all these zeros, let's call this 0, 1, 2. So this is 0. Oops. This is 1. And we don't need these little pipes anymore because they're just method calls. So this is KS1, no dupe, and this is KS0. This is KS2 is a permutation of KS1. I'm just looking at the number of primes, number of apostrophes to rename it. And again, this is so we're setting up like a little pipeline basically. All right, so we'll call this KS1. Okay. I see why I flipped it over. I don't need this ever again, so I can call this just this. And I could even put this here and say, not even this, but I think that should work. Right, because I'm passing this value. So this produces a value. I pass it to this function, and then whatever that produces, then I pass it to the rule. This produces an if. Can I see how it moves? No, I don't think I can see how it moves. I can't see the intermediate results just by tapping around like that. But that's fine. This is good. This is good enough for me. And I think I can say KS1. Can I do that? Yes. And so here I could say KS0, no. Nope, something's wrong. It didn't respond. It didn't, because let's restart it, see what's happening. I'm waiting for this yellow bar to move down. There we go. Okay, so now I know it's good. But it wasn't responding. And now if I put a 2 here, then it immediately gives me an error. But it wasn't doing that a second ago, so I was paranoid. And I think, since this is a list, I can say that. No. How about this? I'm not thrilled about this little sequence of stuff here. Because it would have been nicer to just write the pipe, right? But Meh. All right, so then what is, how do we know that the size is the same? Because the dedupe step could, in theory, it doesn't matter if the size is the same. It matters that the size is not 0. So we could say like length dedupe or length of no dupe. I think if I have this, the saying this is a cons operation, I think, let's keep that up on a page, and then we'll say we'll look for length of cons. And I think, yes. So I can now say that if it's a cons, then the length is not 0, which is all I need to prove. H size, what do I have to prove? I have to prove that the KS length is greater than 0. And usually you write it like this. I don't know. It's just better to write things with less than in Lean. I'm not going to change this one because it might be broken. Okay, what's going on here? It's stopping again. I'm going to restart this server because I think the Lean server is just bugging out here. Give it a second or two. I'm gonna grab a drink while I wait for this. It'll take a minute. This chair hurts my back, so I have a little thing behind me. Okay. All right, so we're back on. Hopefully it's a little faster now. I keep adding this and removing it for like exposition, but okay, so I don't. Yeah, it seems pretty fast now. All right, so so the question was, what is Rake? I wanted to see what this was. Still not like the syntax highlighting is a little weird. I'm going to restart it one more, just the file, not the whole server. It keeps a lot of stuff in the cache, and that's why it goes faster once you. Huh. You see that the S is not same color. It's because like the editor does a syntax highlighting pass, and then it gets some semantic information from the server, and like these will change colors based on like the blue, the cyan means that, well, basically that it's defined in terms of this thing, or it's you know, like you're introducing a thing that isn't what am I trying to say? Well, I guess it's local to this definition is what it means. I think even this little underscore 2 should be blue. I don't know. Okay, so anyway, so have h size is that ks2.length 0 is less than ks2.length, and that we prove by some other long proof. Let's see if ESOP can solve it. No. Well, let's see, what we can say 0 is less than RKS, how about KS0 dot length by, and this is map of something, some rule about mapping. Oh, it's called list length of map. And we say simp. No. Length of map F. R.ks length map F. No, it's not quite right. It says it has type dot length equals what is expected to have. Oh, right. So RKS length equals RKS length, R.ks length, which is this. We don't need the, again, by exact is always a redundant. Have KS1 length. So what do we do in KS1? We dedupe it. Is greater than 0. I don't know how to prove that yet, because you're removing things. So how do you prove that it's still at least 1? Oh, but I do know how to prove it because it's well, I'll get to it in a minute. It's we have to unfold these two things. That's what I did. So it's in ks2 dot length is equal to r.ks length. No, sorry, is equal to ks1 dot ks1 dot length, and that is a property of merge sort. So list length of merge sort. Merge sort with capital that, and again I have to put in the relationship. Really, any relationship should work. and then fill in KS2, KS1. In fact, I think I can again say this, merge sort, and then fill in the blank. Yeah, no, it'll just fill in the blank for me. Like that would also work. Okay, and then from this is redundant for now. I suspect I'll need it in this proof, but right now that's redundant. And then between these two facts, we can just say it's a transitive property. And so we can say exact, and it'll give me some little thing here. But it wants these to have names. So we'll call this H1 and H2, and just rewrite it again. That seems unnecessary. So here it's the exact is doing something, right? I don't know why that didn't turn blue. There's something wrong with the syntax highlighting. All right, so now how do we prove this? All right, so this is H size. All right, so that all works. So the only thing we have to prove is this sorry here. And if we change that to by sorry, then we can put the sorry on the next line, indent it, and then now we have like a little gap. Well, the logic here is that the length here is greater than 1. Right, so we know that the I guess there's like a rule that I want to prove that would be like a lemma that if you have some, so we'll call it dedupe, length of dedupe. So length of dedupe, where n, or we'll call it x's, is a list of nats, and let's call it x is 0, or x0 and x1. X1, so we need, okay, so we have x0 and x1 are both lists of nats. And they're just going to be we're not going to pass them in directly. And then we're going to say oh, I see. Yeah, so we're going to do it. Rather than having an explicit x1, I'm just going to make the theorem. I was thinking about how these theorems work. And so rather than having an x1 and x2, they just have the L and then the expression of the L. So we'll say we'll do what they do and follow their convention. L is a list of nats, and then what do we want to say? That L length greater than 1 implies, or greater than 0 implies that L that L dedupe length is greater than 0. And maybe we'll write it like this. It's just sometimes easier to always use to have everything in the same, to go in the same direction. And then the proof of that is by sorry. But what do we do in the middle? We're going to say unfold dedupe. We're going to unfold L.dedupe, list.dedupe. There we go. List.pw filter. That's not what I was thinking. Let's see. I was looking at these, right? Oh, dedupe equals cons. What is it saying? It says that L dedupe equals A. So if we can destructure A into oh. Maybe that isn't helpful. This is what length means, right? So cons length. Length of cons. All right, let me retrace my steps. What I thought I saw. No, we're going. All right, so we're proving here. First of all, let's this should now trigger that somehow. Right, so it doesn't, because I haven't proven that k has 0 length, or rather that have ks 0 dot length is equal, or 0 is less. He can't find it. Have r dot h size. Now this should find it. No? Omega? That's locked up again. That should be what is, let's say RH size R dot yeah, but it's not doing that. Okay, it liked that. Okay, and then I want to say simp this at HR size. So taking this fact and using it to simplify this. Okay. But if these two are the same, then this should be. I can rewrite this somehow. Oh, because the problem is that it's a K instead of an H. There we go. No. What's wrong with that? Ah, I see. But right. So it's I have to rewrite it and then I use the fact. Then I have to say exact. Okay. I think maybe I can do this conf HR size. Mm-mm. Well, this is what us allowing it to work. Let's just do that. And then I don't even need that RH size. We can get rid of that. And we can even inline this. .sim, right? Okay. The important part is the left-hand side. So if the right-hand side is, like, it doesn't really matter to me. Like, if this function gives me that, I don't care if this is readable. It doesn't really matter to me as long as this is readable. So we'll call it H0. So if I can fill in this step, then I'm good. And just for golfing purposes, oh no, I can't. I was going to say I could switch these two around. I don't think I can. Right, I'd have to pipe this through .sim. And all that was just to remove that. Let's just do it like this. What do I do here? I'm going to wrap this up pretty soon. I'm getting tired. So maybe after I finish this, I'll clean it up. The idea is this. So this length.dedupe. So maybe actually I can find that exactly now. Yeah. Okay. All right. And in fact, we can again remove this. Okay, so that's relying on this. So this is the general proof. Okay. So let's intro H0, or maybe just H_len for the length of the original list. Right? We're introducing this, so we have that fact. Maybe this already exists, so let's see if it's out there. I don't think it is. I couldn't find it. No. Okay, so unfold LD do. Can I just say .dedo? No. Dedo? No. List.dedo. What is PW filter? Pairwise. I think I can get there from here. But I have to say, like, cons of length, maybe? But not this. Cons length? What am I trying to say? That length. This is what I want. All right, so from this, I have this fact, so I can apply that to something. So So if 0 is less than L length, which is what I have right here, HLN, then I can say I apply this theorem. I want to say check in here, print or something. So we can obtain the head and the tail. Obtain head, tail, which is this. So it asserts that the head and tail exist. But can we even say like this? Head, tail? No. So there should be three things: H, head, tail, and H, neck, whatever. Right? That they're. Oh, but you want these brackets, the destructuring brackets. So we'll call H cons. And if I'm thinking correctly, then I should have two. Like I should have an object, a list, and the assertion that yes, the list is equal to that. That's what I need. And then from here, I can rewrite, I can use this. All right, so we can, so this is L dedupe. I can rewrite that. I can rewrite, so rewrite hcons. Yes, so now it changes to that. It changes the L to head cons with tail. And then do I already have that? Yes, I've used that one. Now I need to use this one. Oh, the hypothesis is that A is an element of L. I think that's not what I want. This is promising. I didn't explain why this did, so I feel like this is not going to work. Well, maybe, first of all, let's just try exact. Because the goal is now to... Okay, so what I want to say is that have HD is an element of L by exact, by, you know, some H cons right here, H-cons, right? No. I need something that says like cons L cons mem. Head mem. Yeah, probably this. L head H is an element of L. What is head? What does this mean? L head. What is L head? List dot head. Got to be able to put this together. So let me try a different search. I might come back to that in a second. Dedupe. Dedupe. And then there was head member. So have list length on something like that. Something about exist, right? List exist length. Right, we have this. I have this already. I have a head and a tail, right? So head is a member. I already have this. I have this. I have this. This is my theorem called H cons, right? All right, so we can rewrite list dedupe cons Yeah, I can't apply that. Okay, so oh, maybe I want this instead of this. Does it matter? Because here it says just A is an element of. So let's do this. So say obtain just E and then H element, which is boom. We'll call it mem. mem. E is a member. And again, I have to use these brackets. Of h length. Ooh. I see, because it's a so I need the dot mpr. No, I need the dot mp. Modus ponens. And the reverse of it. So it's just, you know, the two arrows point in different directions. So one is mp and one is mpr. Okay. That's called L. So an element and H element. Okay. So the L is an element of the list and it's a number. Okay, so now going back to this, so there was some dedupe of I kind of want both of the facts. I want the fact that it's right. So I want to say like cons mem. List.cons mem. How about mem of cons? Yes, okay, this is what I want. A equals B, or A is an element of L. A is an element of B. This is what I want, self. A is an element of A cons L. Right, so now, so have of H cons. So head is a member of H cons. No? So that's so I need not H cons. I need that it's a member of L, and that is by this. I bet I can just say exact and it'll find. Nope. This memcon self head L this is the thing, and the question was head is an element of head is an element of head. No, that's not what I want. What I want is this. Head is an element of L. And now if I say exact here, it'll give it to me. No. By exact. Still no. But I can rewrite L with H cons. Okay. Yes, and now it's that. Now that the rule I was just looking at. So So the idea is that we start with, we have to prove this because we just said we want to prove it. And then after we rewrite that rule, the L becomes replaced with head and tail. And then the exact rule that I just looked at applies. Okay. And now we can rewrite. We don't need this one. So we can say L dot dedupe is equal to head tail dot dedupe. Yeah. Why is that true? Right, because, okay, so yeah. Cons of mem. It's true because this is a unique element, and it's the first element. Okay, so I'm close. I gotta see what this is. Oh well. I bet there's other ways to prove that. Hmm. But okay, so I didn't even need that fact. I'll leave it here for a second. I think I can get rid of it. Did I even need? I did need this fact. All right, so then I think I use this in reverse. Well, okay, but no, it would be something slightly. There's probably another theorem that's like that. So we'll say we're going to look for something like list length of cons, right? I think I even had that before. Length of cons. Length pos if exists con. That's what I already had. That's what I saw. Which is what the goal anyway. By exact. No. I just got to find the right way to put these together. Not length equals 1. I see. So yeah, I wasn't sure you could do that, but you can. So we just say use head tail, right? LD dupe equals head dot tail. No, that's wrong. This is something. No. No, I think this is wrong. I don't. This is wrong. I want this. Uh, and that should be a theorem as well. That's totally a theorem, but I'm not seeing it. I just saw it a minute ago. Okay, so dedupe cons this. Okay, cons of, all right, so I have oh, I see. So I've got to say something like this. That head dot tail dedupe is the same as this. By head dot tail dedupe is the same as tail dot dedupe. I can't apply it because it's because I don't have the fact that it's a member. All right. Oh, but I have this fact right here. Okay. And then from that, I can say have head is a member of tail.d2. By rewriting this in reverse, so mem d2. Simp mem d2 in reverse. To the left. I would say rewrite. Add this. No? A is an element of L. D2. Head is an element of list. Should rewrite to head is an element of LD.D2. I may have to say list dot. Yeah, like this. Okay. So from here I have head is an element of L.D2. And then from the fact that I have an element, yeah, there we go. Then we say list positive mem, and then so the fact that we have a member gives me this. And that's all I need. Length pos of d2. Yeah, so I had commented this out thinking that I might just leave it out of the definition for now and then do a pass and put everything in there. But I think this is fine. So I think it's not going to be hard to do this. So I'm just going to leave it in. So h unique is equal to is it h unique 2? I think I can just say R ascending here. Right? Yeah, that's all I need. Maybe I will call that ascending terms. All right, so I'm going to go to bed in a minute, but just stub out what's left to do. So we need Do I use this anywhere? Because this will not be true anymore. Yeah, it's never used. Just going back, I'm pretty sure I didn't use it in LeanSieve. Just to be sure, we'll start this file. Come on. Busily processing. Oh, there we go. Yep. Okay, so that's all good. No red lines, no yellow lines. Yellow means you use sorry somewhere. Red lines mean you have an error. I will have to rewrite all this once or I may have to rewrite some of it. It just depends on what theorems I'm relying on. But you can see the ideas are pretty much the same. We have H sort, H size, and I added a new thing. And I did change it from H sort less than or equal to H sort less than. But I think in general, it should be easy to convert this over. I'm not expecting any trouble at all if I replace Rake with Rake Prime. But did this get me any closer to proving this? Because this is the thing that was most important, right? I'm going to spend just a couple seconds on this. It'll probably be more than a few seconds. But let's say by unfold rake.term. Oh, we're going to use Rake Prime. I'm just expanding all these definitions, and then we're going to say dsimp. Just gonna get. I don't think I can simplify that. Yeah, just simp would do that, right? Same thing. All right, so we need. Oh, let's call this the remainder, and we'll call this the quotient. So MQ is going to be M divided by. Let's even give this a name, like say set len is equal to, how about KL is going to be the r.ks length, ks.length, and then this we'll just call this KL. I'm just simplifying the definition so it's easier to see. I might reverse that later. This follows from the definition of, but you have to expand it. That's the problem, is it, like Why is that not true? Yeah. And same thing. Yeah, so that just didn't really help me anything. Anyway. Okay. When you do set, it's supposed to rewrite things. Like it's supposed to be rewriting that, but it's not. So I'll just rewrite it manually. Show r.ks m remainder HMR plus r.d times mq less than r.ks nr hnr. Like all of that was just so I could read it. Maybe it was not necessary to do all this. What? I just started at the very beginning and said like eSimp. Simp. I don't have any simplification rules. Well, the question is by cases whether MR is equal to NR. Well, if it's true, let's call it H. How about H equal? How about H R's are equal? So the R's are equal. If it's true, case pause, then two terms of the same sequence. Then we can rewrite the goal in terms of hrec. Why not? The hrec is that MR is equal to NR, so why not rewrite that? Why can't I rewrite that? Motive is not type correct. Maybe it's because, right, so they have different. So we want to say have r dot ks get, or just rks mr from hmr is equal to r dot ks of nr and justified by hnr. You have to prove that you're not out of bounds, right? So and that's what's causing it to not be. I believe what's causing it to not be congruent. Like that's why I can't do this rewrite. No. Yeah, okay, that worked. And then rewrite. Why can't I rewrite this? All right, so now we can rewrite it. And then now we can simp. And because we can cancel those terms out. If we have we don't know that. We don't know the fact that R is greater than 0. That D is greater than 0. So H, what would we call it? H delta? H0? Or how about D pos? H D pos? Right, so now if we know that, now we have to fix all these places where we didn't say it. So we say H D pos equals by simp. And then down here we do the same thing. Pos equals by simp. Actually, that is exactly the same as R dot D pos, H D pos. Because we're inheriting the fact from R when we create the next one. And that's it. Um, yeah, I was going for this. Maybe I didn't even need that. Maybe I didn't even need this fact. Where did it go? Actually, I think you can say simp this. And then sometimes you bring the rule into scope and then do the search with like rewrite or whatever. And then once you know what you, like once it's in scope, it can use that to find the rule that you want to use. And then yeah, this right here. And then once you've done that, then you replace the word this with the simpler version of it, because it's just a one line, or it's just a simple thing here. Yeah. I wonder if we can just merge those together. Yeah. Okay. So this is going to be hard for me, but it's not that hard. It's just it's a matter of every time let's see, dsimp mq nq. So I think I might have proven this already. So I have a whole file of things. And I thought this was incredibly hard to prove. But let's call this, but it wasn't hard for somebody else to prove. It was hard for me to prove, but somebody else found it like almost instantly. Like when what I want to do is I want to say that call this hmod. Oh, okay. So what this does, what this is meant to do, so we're rewriting, starting with this, and then we're rewriting, we replaced M with this thing. And this thing. We need to say have d times m over d is equal to m. Is that true? No, it's not quite true. You would think it'd be true, but it's not. It's not true in no. Ah, I see. But I'm proving the wrong thing. I want to prove this, that they're equal, and then by this. So now that I should be able to simplify with this with hmod. so comment that out. Stop the omega. Broke something there. Yeah, okay, so now this works. In fact, did that solve? No, I haven't even gotten there yet. This hasn't gotten that far yet. Come on. I don't think I even used Slim Check or QFI. I don't even, because it says import method, that's why. Let's restart the file. When you import MATLAB, you get so much junk, it just takes forever. It is almost 5 o'clock in the morning. I should not be doing this. There we go. Okay. I think you can do the same thing now. But we might have to do something to cancel it. We'll see. We have to add the right. Yeah. Add HMN. And that's almost the same, but I don't think it's quite the same. Let's see if we, yeah, so now let's see if we can do exact. Yeah. Like this. Anything involving division has historically taken me just forever to solve anything. So much so that I created this file and printed out a bunch of. Oh, I did have Slim Check in here, but this is garbage. Like you can see all these like false starts and stuff. But I'm going to delete that. Actually, let's delete everything below here. And then we'll make a new, I'll put that in a new file. And we'll call that something else. How about natdiv scratch? We'll add that to Git. And maybe instead of adding it, I might just copy the theorem I need for now. I don't necessarily want to commit this right now. What's wrong with that? because they're not, so we say M, N are nat, and M, N, and D are nat. And we have HD pause, which is that D is, the 0 is less than D. And then we can prove that. And then from this fact, I believe we can say we can use that fact, that proof up there to solve it. No. All right, so have KL is greater than 0. Have 0 is less than KL. I'm going to finish up this side of it, and then I'm done for the night. I still have to do case neg. Case neg, sorry. Is equal to r.h dpos. Nope, that's not what I want. I want h size. And then this. Why didn't that work? All right, say well M and D, and then we have to know that KL, we have to know that KL is pos, which is this, and then we have to know HMN. What? No. KL pos. I don't know why I'm not able to unify with that, but maybe. No, okay. There's something going on here. It's slightly wrong. Does this produce this? M is less than N over D, so we're going to do the exact, and it's M, N, and KL. D is KL. And then we have HD pos, or HKL pos. Dsimp mrnr at h at this thing right here, hrec. There we go. I wonder if I can even say it the easy way now. No, it still doesn't like this. Nope. So you have to say it explicitly. Interesting. Hmm. I'm just curious if that makes any difference. No, it just doesn't. Interesting. Okay, well then we have this other case, which is this is the idea that they're not equal. So these two things are not equal. But we do have these two things. The implication is that if these are not equal and this is less than, so these are not equal. I might have to do another one of these little proofs over here. I don't quite have this. I have they're not equal. I have m is less than n, and these are not equal. Or rather, these are not equal. Right. So then the trick would be, see if I can prove it, just real quick. If they're not equal, then yeah, I don't know. See, this should be like a stronger thing. That's not just an arrow, but a left and right arrow. Because I have this. Oh, no, but I don't have less than and that was one of the things I was trying to prove. And the person who helped me suggested I simplify it to this, which is just the right arrow. But I need both. Right? Alright, so I need to have if you have the left arrow, oops, left, and then you swap these. What's wrong with that? Right. Sorry. You still have that. Yeah, right. Okay, so this would be div equals of less than mod less than, something like that. And we call this hmod. Hmod. Oh, but it's not equal, so you can't use it. And we're back here, and so we can't do assumptions. We can just rewrite. And then you have to show this by something else. I feel like you ought to be able to subtract something from both sides of this, but I want to see. Oh, let's see if you can do this. Have d times m over d is less than d times n over d. Yeah, I can't find that. Wait, hang on a second. H mod at HMN. Like, because this is less than that, yeah, so we can use this less than add if right something. Have a rule. Let's say let rule. What? What's wrong with this? Something plus something is less than something plus something else. HMN. We should be able to rewrite this. Yeah, that's not the right rule. Okay, so what do we want? I don't know. This could take me hours. These are really tedious. So what I need to do is look at the rules and just really find the rule that gives me what I need. I don't even need this one, right? Like, this is the one I'm working on. I don't know how to progress from here. I'd have to look at the rules and like dig through them, and I'm just not. I don't want to spend a lot of time on this. It starts 5 o'clock in the morning here. All right, so I'm going to move this to Scratch for now. The Scratch file over here. Oh. Close it, I guess. So all of these pass. So as long as I guess I will check this in. No, I didn't. I don't need to. If you check it in, if I check it in, I have to change the Lake file and register it as a class. So I'm just going to leave that as a Scratch file for now. All right, so I got one error here. What's the error? Probably that it didn't get proven. So just delete this because I was going to use it, but I haven't gotten it yet. All right, so we're no worse off than before. The main thing I did was I implemented this proof and added this type signatures for these. And the hope is that, and I did some of this. So the hope is that I can fill this out somehow. So what I need just the outline here. I know I said I was going to bed. I am. Have MQ is less than NQ. Sorry. Because M is less than Q and or M is less than N and M mod Q is less than, or N mod and MR is less than NR. But I don't have a theorem that proves that yet. Maybe I do. Yeah. It's actually decent is what I'm looking for. All right, so forget that. But once we have that, then we're going to say exists a case such that MQ plus K is equal to NR. NQ equals exact by exact. That's got to exist. Huh. The ESOP has just not been giving me much to work with here. You would think that would follow directly from this. That MQ plus K is equal by like something like, I don't know. Sorry. Because that's what less than means. Obtain K sum equals this. And then we can use that dsimp this, not this. Actually rewrite ksum at what? Maybe just rewrite ksum. There we go. And then we can apply simp only this. Oh, well, I guess that's not it. We have to apply apply nat dot mul dist mul add yes. How about simp? Yes, that's what I wanted. And then once we've converted that, I learned how to use this a little bit. RD times MQ plus RD times K. Then I wonder if we can just simp all. Or just simp. No. Nat mul com. I wonder if it works like this. I don't know how to go back up when I'm doing these rewrites. Up, back. No. So we'd have to do it again. There's probably a way to do this, but and then So it would be nat add source, add com. And that switched to, I don't think that's what I wanted. I think I wanted added. No, that's not what I want. Yes, that's what I wanted. Wait. That's what I want. I wanted this thing on the side. I want the RD times MQ on the right hand side. Now RD on, how can I simplify that? Yeah, that's what I wanted. I only need simp only. Can I even say RW? Yeah, so even that. I think maybe this is I didn't need this theorem about division to get to this point. I think just the fact that this is less than this follows from the fact that the thing is sorted. Like whatever rule I use to derive this should be the same rule that I use to derive this. Oh no, because I can't manipulate the goal to get that because it's not true. We don't know that it's true yet, so I can't. I make that mistake a lot. I think I can manipulate this, like derive something from this by simplifying it, but no, you can't because you don't know that it's true. You're trying to prove it. Um, but this is by something about H sort. But by sorry, this is a consequence of um, r dot H sort. Right, and this is a positive number, so like, that ought to be, yeah. So if you add something to it, then it's good, and then that's it. So that's the proof. But I have to fill in these three things. And I've justified them informally here in the comments, so I think that's reasonable. Okay, so I'm going to save this, and then I'm going to call it a night. All right, so we'll save. Just oh, did I do this tonight? Yeah, I did. Okay. I don't remember if I did this on camera or not. I don't remember when I turned the camera on. But I guess I've been doing this for long enough that it was about it's 4 hours. Hopefully, I got this many proofs done. Okay. Yeah, let's just all right, so we say just Rake working towards in Rake prime min term 0. Yeah, so in order to prove this, I have to prove this, and just how about say Rake prime gt and start on in term 0. All right, well, thanks again for watching me ramble for 4 hours on. I think I hope this one was a little more informative because like it's actually I'm learning more on this. Like I feel like I'm getting a little better at using Lean, and also I'm so every time I show something, it's like I'm not struggling with the most basic problems anymore. So hopefully it's a little more educational. Far from being an expert, I'm far from fluent in this right now. I think you can become fluent, but yeah, not today. All right, well, have a good night, or